Okay, so at the center of calculus is this concept of a limit, right? So usually when we think of a limit, we think, limit of f of x as x goes to a is equal to L, right? And so what this means is that we can make the value of f of x as close as we like to L by taking x sufficiently close to a, right? So I don't know if this will show up very well, right? So, if we have some value a here, right, and this is our function y equals f of x, then if we're traveling along the curve or close to a, right, so, somewhere around here or maybe over here, walking this way or this way, right, then we expect to get closer to this value L, right? So we can make f of x as close to L as we like by taking x sufficiently close to a, right? And this, of course, is just specific to this drawing is specific to L being a real number, but we could also have a limit being infinity, and we can have a limit at infinity. Right, so if we have a limit at infinity, right, so we're taking the limit as x goes to infinity, then if that's equal to the number L, right, then it looks something like this, and we have a horizontal asymptote of L. And if we have a infinite limit, so we're taking the limit of f of x as x goes to a, and we get positive infinity, then it might look something like this. So you'll have a vertical asymptote in this case, right? And we can also have a limit that is equal to negative infinity as well, right? Now, one of our first introductions to the limit in Calc 1 is through the tangent problem. So that's where we figure out how to find the slope of a tangent line to a function f of x at some point x equals a, right? So we want to find the value of m here, right? So normally, or before Calc 1, when we want to find the slope of a line, we use rise over run, right? Rise over run requires you to know, two different points on the line. But here, we only know this one point, a comma f of a. So what we do is first approximate, and you'll see this, and you've seen this pattern in Calc 1, that we do a lot of approximations, and then to find some exact value using the limit of the approximation. So what we do is we look at a nearby point, maybe over here, right? So that corresponds to this point at x equals a plus h, for small h. Here, just in the picture, we have drawn, h is positive, but you could also take, h to be negative, and it would be on the other side, right? So what we do is we first can, approximate the slope of the tangent line by finding the slope of the line that passes through these 2 points, a comma f of a, and this red point, which is, point a plus h comma f of a plus h. Right, so we find the slope of the secant line, which it passes through these 2 points, is just rise over run, right? And so that's f of a plus h minus f of a over h, right? The a cancels out in the denominator. But you see, at least in this picture, we have drawn, maybe our a plus h is not close enough, or h is not small enough, that this is not a good approximation, right? The slope of this red line is really nowhere near the slope of the black line, right? So we can take another point, maybe we'll use a different color here, right? Slightly closer, right? And then maybe even closer than that, right? And keep taking points closer and finding that the slope of the line going through these 2 points now is getting closer and closer to the slope of the tangent line, right? See that these will just get closer and closer, right? It's a little bit hard to draw, but yeah. So what we want to do is we want to take h to 0, right? We want to use this approximation and just take h to 0, right? So we want to take a limit. So we get that the slope of the tangent line is just a limit as h goes to 0 of f of a plus h minus f of a over h, right? And so this tangent problem is really important because it's what gives us the limit definition of the derivative, right? So we can actually take this formula for m and let a be any real number. So replace a with x, right? And that, as long as it's defined, that limit will be a function of x in its own right. Right, so letting x vary, we define f prime of x to be this limit as h goes to 0 of f of x plus h minus f of x over h, right? We call f prime the derivative of f. We use the notation f prime of x is equal to d dx of f of x, right? So in this notation, we see that we can view the derivative or differentiation as an operation that we're doing on a function f of x, just like addition is an operation that we perform on numbers, right? We come up with rules and laws of differentiation which allow us to compute the derivative of a function f without taking a limit, right? And so that's how we probably recall differentiating functions in general. Is not necessarily through the limit definition, but using the product rule, chain rule, quotient rule, etc. Right, and so we see that we go from the tangent problem into what's called differential calculus, so the calculus of derivatives, right? Maybe you remember doing some applications of that, like optimization problems or related rates. And we know the derivative to be extremely useful just from our understanding of the tangent problem, right? The geometrical importance of tangents. Now on the other side, we have the area problem. And that is going to be a problem that leads us into integral calculus. So the problem is, how do we compute the area under the curve y equals f of x between a and b, right? And so just like we used the slope of the secant line at a nearby point to approximate the tangent line and then take the limit, we're going to use rectangles to fill up kind of inside the region, approximate the area of the region using the sum of the areas of rectangles, and then take the limit of the number of rectangles to infinity and see that we do get the exact area. So now we have that the area of the region R is approximately equal to the sum of the area of these rectangles, right? So we're taking n rectangles, and for large n, right, then this will be a good, decent approximation for the area of R, right? These are equal with delta x, and the sum is denoted over here, right? So the area of each of the rectangles is just height or length times width, right? Area of a rectangle is length times width. Here we could just call it height because it's vertical. So now if we were to take the number of rectangles n to be larger and larger and larger still, we would see that the area inside of the rectangles is getting closer and closer and eventually coinciding with the area of the region R, right? So what we have is that the area of R, which will right here, of R is equal to the limit, right, as n goes to infinity of this sum here, right? So this is not approximately equal to, this is actually equal to. Right, and so that is how we define, right? We define the integral. right? So that's equal to the integral from a to b of f of x dx, right? And you can think of this dx as what it really is a differential, right, which you learn in Calc 1. But you can think of it as kind of like the infinitesimally small width delta x, right? So that's like the width, right? And then the height is this f of x, right? F of x I, right? So counting up I equals 1 to n, right? Those are discrete values. But then when we go down here into the integral, which is defined as this limit as n goes to infinity, we just have f of x, right? So just continuous values of f of x, right? Continuous values of x. So, and then you can think of this integral sign here as like the continuous version of this sum, right? So all of this, these arrows here just kind of correspond to once we take the limit. So now we see that through the area problem, we come up with this definition for what we call the integral. And that leads us into integral calculus. But before we even talk about integral calculus and how we go about computing integrals using rules and laws in the same way we go about computing derivatives, we need to make note of the, fundamental theorem of calculus, right, which tells us that these two different sides here are connected, right? Differential calculus and integral calculus are connected through the fundamental theorem of calculus, right? Oops, fundamental theorem, right? And what the fundamental theorem of calculus says, if you can remember, right, we just call this FTC for short, right, is that the derivative and integral, or differentiation and integration, are inverse operations. So one undoes the other. They each undo each other, right? Just like an inverse function undoes the original function, or subtraction undoes addition, or division undoes multiplication, integration undoes differentiation. And so when we first learn integration, we learn the what are called anti-differentiation rules, right? And so all of that we learn is called integral calculus. So now I just want to emphasize that all of the stuff that we learned from Calc 1, most of that was to serve us in differential calculus, right? That's the main focus of Calc 1 anyways. And we're going to, all that stuff that we learned, we're going to still use that, right? Because even though what we're mostly going to be focusing on, or at least for at least half of the course, more than half of the course, we're going to be working on integral calculus, right? We need all of that information that we learned from differential calculus, because all of our, integration rules will come from differential calculus, because everything we know about integration comes from the fact that it's the inverse operation of differentiation, right? So, and then even going back further, the concept of a limit is going to be a hugely important thing for us, especially in the second half of the semester, right? So when we learn about sequences and series. Sequences, series, and power series, right? So this is also going to be a focus of Calc 2.